welcome students. Once again welcome to the IIT PAR lecture series on logarithm. Today's lecture is a fourth lecture in that series. As I mentioned, now the problems are getting little bit difficult. So now this will let us see what this problem is. It's log to the base some base x upon b minus c is equal to log of y upon c minus a, which is equal to log of z upon a minus b. If this relation is satisfied, then I need to prove that, then I need to show x raised to b plus c, y raised to c plus a, and z raised to a plus b is equal to 1. How will I show this? So now if you look at this expression does not contain log. These relations are given in logarithmic form. So I have to somehow get intermediate step such that I can connect this. So how will I connect this? Just take the green pen. Okay. So can I get an expression in logarithmic form for this particular expression? That means what? That means I will apply a function log on both the sides and I will get some answer. So if I apply the function log on the right hand side, I know log to the base a of 1 is equal to 0. Okay. And if I apply the function log on both sides, then it is log to some base. This a is not the given a. This is just a representative of the base. So if I apply log function, let me put it as log to the base 10. It doesn't matter. So if I apply the log function, log to the base 10 of this particular expression, x raised to b plus c, y raised to c plus a, z raised to a plus b is equal to log to the base 10 of 1. Right. So what will this be then? This particular thing is of the form m into n into p and log to the base some r of m into n into p. So I can apply that extended multiplication law and I can rewrite this as log to the base 10 of x raised to b plus c plus log to the base 10 of y raised to c plus a plus log to the base 10 of z raised to a plus b. It does not matter whether this is 10 or not, it is some representative that I am taking, and this is equal to 0. So I am rewriting this expression. So this is if and only if this is valid. Now this expression is valid and therefore I can use a power law, which is a log to the base a of m raised to n is equal to n log to the base a of m. So I will use the power law, which will give me b plus c log to the base 10 of x plus c plus a log to the base 10 of y plus a plus b into log to the base 10 of z is equal to 0. Right. Now you just look at this expression. I cannot use this expression as it is, but what I can do is I can use the power of ratios and say that if all these ratios are equal, then let them be equal to some w, that is log of x upon b minus c. So I have simplified the side which I want to show. Now I am taking the given and now I am trying to simplify the given y upon c minus a upon a minus b. Let this be equal to some w. Okay. That means what? My log x, if I take log x, it will be some w times b minus c. If I want to take log y will be equal to some w times here c minus a, and log z will be equal to w times a minus b. Okay. If it is this, then can I substitute this for the expression which I simplified? So let us for brevity, let us say it's log to the base 10, 10, 10. It doesn't matter, this is just a representative. I can put any base. So now if I can do that, then I will substitute these values in place of log to the base 10 of x, log to the base 10 of y, log to the base 10 of z. Okay. So what will it be then? Let me say this expression to be star. Then I will put these values, all these values, let us say double star. So putting double star in star, what do we get? So it's b plus c times log to the base 10 of x, which is w into b minus c. So let me write b minus c into w plus c plus a as it is into c minus a into w plus a plus b as it is into a minus b into w, which is equal to 0. What does this mean? We already know it is w in common, b square minus c square plus c square minus a square plus a square minus b square, which is equal to 0. So w cannot be 0 because it is a ratio of something. So w is non-zero. So now if at all this has to be true, this ratio should, this particular sum should be 0. So am I getting this? B square with a negative b square, c square with a negative c square, a square with a negative a square. So I am getting this to be equal to 0. So basically what I am getting is w into 0 is equal to 0, which is valid. Therefore I have shown that if this relation is satisfied, these terms will equate to 1. Okay. I hope it is clear. Now let us try to solve another example, which is say 6. It was 6. Now let us make it. Let us find 7th one. 7th problem. Okay. 7th problem is, it will be simple, but 7th problem is again that equality problem. If a square is equal to b cube is equal to c raised to 5, which is also equal to d raised to 6, then show that log to the base d of ABC is equal to 31 by 5. Okay. This is interesting. Now again, since everything is equal, I will put this to be equal to some number, some constant. A square is equal to b square is equal to c raised to 5, b cube, sorry, it's b cube c raised to 5 d raised to 6 is equal to say some k, and then I will start solving the problem. Okay. I will start solving. That is okay. Then how will I handle this? Then I will actually write everything in terms of k. So if a square is equal to k, then my a must be k raised to half. If b cube is equal to k, then my b must be k raised to 1 by 3. Okay, and if c raised to 5 is equal to k, then my c must be equal to k raised to 1 by 5, and my d must be k raised to 1 by 6. Okay. So once I have this transformation, I will substitute all the values for the left hand side of the to show expression. So it's log to the base. Okay, let me write first the expression. D of a b c will be equal to log to the base. Now I will substitute for d, which is k raised to 1 by 6 into a is k raised to half, b is k raised to 1 by 3, and c is k raised to 1 by 5. So this is equal to log of k log to the base k raised to 1 by 6, k raised to half plus 1 by 3 plus 1 by 5. You can calculate this. And it will be log to the base k raised to 1 by 6. So the what will be the LCM? 5 into 3 into 2, which will be 30. It will be 30 upon 5 into 3, 15, plus 5 into 2, 10, plus 6. And this k raised to this thing. Okay. So log to the base k raised to 1 by 6. I think this should come out to be 15 plus 16, that is 31 upon 30. Okay. So according to our power law, this should be equal to 31 by 30 into log to the base k raised to 1 by 6 of k. So I want to find this answer. How will I find this answer? It may be difficult to find, but I have one rule which I have not used so far. It's a change of base rule. So I will try to use. I think I am getting the first opportunity to use the change of base rule. What does the change of base rule say? If I have two expressions, m and n, or a and b, say log to the base a of b, then I will put the argument in this, and I will put the base in the denominator, and I will take any common base, say c, right. So I can use this change of base rule, and I can try to simplify this expression. So it's 31 by 30, and the change of base rule, log of k upon log of k raised to 1 by 6. Now the base is at my hand, so I can choose any c. So which c I will prefer? If I prefer k as a c, then my calculation will be simplified. So what will happen then? 31 by 30. What is a log of k to the base k? It's 1 upon, what will this be? It's a power law, so 1 by 6 will be thrown out. So 1 by 6 into log of k to the base k. Okay. If it is so, then it is 31 by 30 into 6 upon 1 into because this is 1, so it will be 1. So 6 5s are 30, so this must be equal to 31 by 5, and that should be the answer. Let us verify. Yes, that should be the answer. So it is correct. So we have proved it. So this is the first time I think I have used the change of base rule. Now let us go ahead and solve some more problems which will require change of base rule. If the change of base rule is not there, then the problem, solving this problem would be a messy task. So it was a 7th problem. So now let us take the 8th problem. Let me change the color. I am using brown color, so let me choose. So this question, if you understand it from the perspective of change of rule, it will be easy. If you are not able to understand from the change of base rule perspective, then it will be difficult. In fact, this is a very easy question. Log to the base 4 of 5 upon log to the base 4 of 11. It's a cooked up question, so just see how change of base rule helps. So now I have something which is of this form: log to the base 2, log to the base 2, 5 and 11. So now, since both these share a common base, I don't need to change the color in this, it is very easy. Since both of these share a common base, what will this be? Log, if I use change of base rule in a reverted manner, so I am coming from right hand side to left hand side, so it will be log of 5 to the base 11 minus, what will this be? Again apply the same logic, bases are same, so I can write this as log of 5 to the base, not 4, the denominator is 11. Then what should be the answer? Equal to 0. Right? As simple as that. But if you don't have change of base rule, then it will be a messy answer. Okay. Now let us try to evaluate one term which is complicated, but again using change of base rule, it will be very easy to evaluate this term. So it is log of v, some v, square root of u cube, it is not square root, sorry, 4th root of u cube into log of w into v raised to 5 into log to the base u of 5th root of w raised to 4, and I want to show that this is equal to 3. Is it true? So the expression looks messy. So first of all, I will use the power law and simplify the expression. I have product of logs, not the log of a product. Okay. So I cannot use multiplication rule, but I can use my power law. So let us first write LHS and let us write it in a civilized manner: log to the base v of u raised to 3 upon 4. You know this, right? Then log to the base w of v raised to 5, there is nothing here, all these are multiplied, into log to the base u of w raised to 4 upon 5. So this, if I use power law separately for each of the log terms, what will this yield? 3 by 4 into 5 into 4 by 5. This, all these are coefficients now for the log, into log of v, log of u to the base v, sorry, log of v to the base w into log of w to the base u. Okay. Now if you look at the coefficients term, 4, 4, 5, 5 getting cancelled. So I am getting 3 into log of u to the base v into log, I am keeping it as it is, log of w to the base u. How to simplify this? Right? The only answer is change of base, and I think I got the coefficient here. So my guess should be this answer should be equal to 1. Okay. So how will I get that? Let us see. So I am applying change of base formula now. So this will be equal to 3 into change of base is log of u, some base a you take, log of v, some base a, log of v to some base a into log of w to some base a into log of w to some base a upon log of u to some base a. U, log of u getting cancelled with log of u, log of v getting cancelled with log of v, log of w getting cancelled with log of w. So easy. So it is 3 into 1 which is equal to 3. Therefore we have proved this. Okay. Let us now see one or two more problems. Just say 10. So again the same set of techniques will be used. I have log to the base 6 of 7, and I am asked to show that this is equal to log of 7 to the base 2 upon 1 plus log of 3 to the base 2. How will you do this? One way is to write this log in log as log of 2 to the base 2. That is one way to answer this. Another way is can be more intuitive, is you can actually start with LHS and try simplifying LHS. Okay. So it is log of 7 to the base 6. Use change of base. What base will you use will be dictated by what term you have in the right hand side. So you use base 2 now. So log of 7 to the base 2 upon log of 6 to the base 2. Okay. Then I think we have almost solved the problem, because I know log of 7 to the base 2 will remain unchanged because it is there in the right hand side. So what I need to resolve is how log of 6 to the base 2 can be defined. But I know 6 is 3 into 2. So I will write log base 2 of 2 into 3 is 6. Therefore log of 7 to the base 2 is equal to log 2 to the base 2 plus log of 3 to the base 2, which is equal to, I think, our right hand side, because log 2 to the base 2 is 1 plus log 3 to the base 2 is 7. Okay. So this solves another set of problems. Now let me change the color, let it be brown. Okay. And we will try to solve more problems where they are just of the form to show, given some forms you have to show. So x is equal to log of 6 to the base 12, y is equal to log of 12 to the base 18, and z is equal to log of 1824. Okay. And I want to show that one plus x into y into z is equal to 2 into y into z. Okay. So this is my problem, and I think this is question number 11. Yes, this is question number 11. So how will you solve this problem? If you see the pattern, 6 2s are 12, 6 2s are 12, 6 3s are 18, 6 3s are 18, 6 4s are 24. So, there is some pattern that is emerging out. So, I have then if there is such a pattern, then definitely I have to use some change of base formulation. Let us now try to resolve this problem by taking the left hand side and right hand side for this to show equality. Okay. So, let us start with LHS. If I show LHS is equal to RHS, I am done. So, I am starting with 1 plus x y z. Again the equation has 1. So, we have to be little bit careful. Let it be 1 as of now. So, what is x? Log of 6 to the base 12 into what is y? Log of 12 to the base 18 into log of 18 to the base 24. Okay, great. Now, I will rewrite this using change of base formula. So, it is log of 6, I do not care about the base right now, log of 12 into log of 12 upon log of 18 into log of 18 upon log of 24, right. So, whatever may be the base, log 12 cancels with log 12, log 18 cancels with log 18. So, now this must be equal to 1 plus log of 6 upon log of 24, right. So, this complicated expression now reduces to 1 plus log to the base 24 of 6, right. Okay. Now, if I want to simplify this further, I will use the power of 1. What is 1? Since I have a base 24 here, I can write 1 as log to the base 24 of 24. So, this is log to the base 24 of 24 plus log to the base 24 of 6, which will be equal to log to the base 24 of 24 into 6. Okay, this should be equal to 144. Log to the base 24 of 24 5s are 120, 24 6s are 144. Yes, so it is 144. Okay. Now, the other party, the other side RHS is 2 times YZ. So, let me do that also. So, I will start with RHS is equal to 2 times Y into Z. What was Y and Z? Y and Z were log to the base 18 of 12 and Z was log to the base 24 of 18. This is equal to 2 times log to the base 18 of 12 and log to the base 24 of 18. Again change of base in action. So, it is log of 12 upon log of 18 into log of 18 upon log of 24. Again I am getting the same thing. So, this is equal to 2 into log 18, 18 getting cancelled. This will be log of 12 to the base 24. Okay. And this is in fact equal to log to the base 24 of 12 square, which is 144. So, I am getting RHS is equal to LHS. Therefore, I have proved this expression. Let me zoom out a bit. Okay. Therefore, I got this expression. Just have a look at this expression. Okay. So, this solves our problem. Now, let me zoom in. So, now let us go to another problem which will again demonstrate the use of change of base. So, this will be the 12th problem of today. Let me change the color, it's brown. Okay, it's 1 upon log of AB into ABC, log of ABC to the base AB plus 1 upon log of BC, log to the base BC of ABC, and the third one will be 1 upon log of ABC to the base CA or AC, let us say AC, is equal to 2. I want to show this, or I will prove that this is the case. Okay. How will I prove? So, what should be your initial guess? So, first thing you look at this problem, when you look at this problem, you will see the quantity, the argument ABC is same for all the logs, but the bases are varying. Do I have any trick which will say the bases are same and the arguments will vary? Do I have any such thing? So, let us analyze the change of base formula, because the only formula that can help you is change of base formula. So, log of B to the base A, change of base formula says is log of any other base B upon log of A, right. Now, what I want in this case is my basis, my argument should be the base and base should be the argument, that is the change switch that I want. So, how will I do that switch? So, I want my base to be the argument, which is done here, right? And this particular thing which is the argument is the argument. If I want to remove this, I will choose the other base to be equal to B. Are you all with me in this regard? If it is so, then what will this become? This will become 1, because log to the base A of A is 1, and this is log to the base B of A. So, what I derived here is log to the base A of B is equal to log to the base B of A. So, it is a switch in the base and the argument, right? And it is a reciprocal of that. Okay. So, I can use the power of this law. This is a very important deduction that you should remember. I can use the power of this law and switch the base to the argument and argument to the base. So, what will happen to the first term if I want to use this power? So, let us take the LHS. So, LHS is equal to, I will not rewrite the LHS, let it be this, and let us try to solve. Something has happened. So, it is A, okay, it has come. So, AB. So, what will be the switch? So, 1 upon log of ABC to the base B will become log of AB to the base ABC. Okay. Similarly, I can use the similar argument for this. It will be log of BC to the base ABC plus log of AC to the base ABC. Are you all with me? What I am doing is, I am using this law, this power law, this change of base law, and converting this 1 upon something to the numerator. So, if this is clear, then what I have is this expression, and since now the bases are same, I can use my multiplication law and get the answer. So it's log to the base ABC of AB into BC into AC, which is equal to log ABC which will be A square B square C square, which is again equal to log ABC the whole square. I will use my power law, which will give me 2 log ABC, which will again give me 2, which is nothing but RHS of the expression. So I have proved this expression. So this is the powerful demonstration of change of base formula. You can go through the method once more and get the answer. Okay. Another demonstration of such a formula is, I have been given that, I have not changed the color for this. Okay. So let me continue with the same color. 13. Another demonstration for change of base formula is equal to, so x is equal to 1 plus log to the base A of BC, y is equal to 1 plus log to the base B of AC, z is equal to 1 plus log to the base C of AB. Then show that xy plus yz plus zx is equal to xyz. See, if you look at the pattern in which the change of base problems are coming, everything will have some cyclic order. So this A is there in the base, then BC is there in the argument, B is there in the base, then AC is there, and this argument and this entire problem involves only these 3 terms A, B, C. So if you get any problem in this pattern, then you should think of change of base formulation. Now if you look at this problem, if you just feed in the values of x into y in this expression, then it will become messy. So before attempting to solve this problem, let us simplify what is to show. So this is equivalent to, if I divide by xyz, assuming xyz are non-zero, this is equal to, if I divide by xyz to the left hand side and right hand side on both sides, then this is equal to 1 upon z plus, okay, let me be precise, I will write the expression. So if I am dividing by xyz, it is xy plus yz plus zx upon xyz. The right hand side will be xyz upon xyz, which is equal to 1. Okay. Then this is also equal to xy getting cancelled, so it is 1 by z plus yz getting cancelled, 1 by x plus zx getting cancelled, 1 by y, which is equal to 1. Okay. Okay, if this is the case, then what I need to find actually is, these expressions which are there. If you look at these expressions for x, y and z. Okay, so I want to simplify these expressions. How will I simplify these expressions? I can simplify them by again using the power of 1. Now I need to choose appropriate basis, right? What is missing here is A, what is missing here is B, and what is missing here is C. So I can put them in this place by using the power of 1. How? I will put 1 is equal to log of a to the base a plus log of a into bc. So this should be equal to log to the base a of abc. Then now similar things I will do here. So this will be log to the base b of b plus log to the base b of ac, which is equal to log to the base b of abc. Similarly, I can do it here, log to the base c of c plus log to the base c of ab, which is equal to log to the base c of abc. Okay. So therefore, now I have the expression of this form. Now what does this mean? So if I substitute the values of x, y and z here, 1 minute, I think the font size has reduced, so let me do it again. It's okay. So I will substitute these values into this expression. Let us see what I get. So again I will get, substituting the values of x, substituting values of x, y and z, we get 1 by z. So it is 1 upon log to the base c of abc plus 1 upon log, it's x, so it will be log to the base a of abc plus 1 upon log to the base c, no, it's y, no? So it should be log to the base b of abc. So what we got here, this should be equal to 1, is the same problem that we had in the earlier problem, in the earlier question, that is question number 12. So if you can look at question number 12, we have something of this form, right? It's a similar problem. So what we will do is this. I will change this ABC pattern into, I will change this pattern, I will convert the argument to the base and I will base to the argument. How will I do? Again the change of base rule, the deduction that I derived in the last problem will give me, this is log to the base ABC of c plus log to the base ABC of a plus log to the base ABC of b. Now can I say this is equal to 1? I can again use the multiplication rule and say that log of ABC to the base ABC, this particular thing is log of ABC to the base ABC, which will be naturally equal to 1, and therefore the answer is equal to 1. Because I derived it, so it is equivalent. So because I derived it from the earlier expression to show, it reduces to this, and then I substituted the values of x and y. So I should have taken the LHS here. So I should not have written this. I should not have written this equal to 1. So LHS is equal to this. Therefore, it is equal to this, and therefore this is equal to log of ABC into ABC, which is equal to 1, and that is what we intended to prove, right? So this is correct now. Okay. Now let us try to solve another problem. This is somewhat simple, but it demonstrates one pattern and derives one important deduction. So let us take the 14th problem of today. Log to the base a of x plus log to the base a square of x square plus log to the base a cube of x cube plus and so on, which is 3 dots, plus log to the base a raised to p of x raised to p, and you have to show that this is equal to p times log to the base a of x. How to show this? So we need a minor corollary or a small corollary of our original problem. First, you have to understand that this is not part of the problem, so I will use a different color and I will try to show it in a different way. Let me take the brown color. So it's what we are actually handling is a problem of this form: log to the base of a raised to m b raised to n. Okay. Assuming all logs are properly defined, I want to express this in terms of log to the base a of b. How will I do that? But from our power law, I can use a power law. I know this particular expression is nothing but n times log to the base a raised to m of b. Okay. If I know this, then I also know something, how I will switch base to the argument and argument to the base, right? So that also I know, I have that law. So what I will do is I will keep n as it is and I will put this as 1 upon log to the base b of a raised to m. This we have done earlier. This is also in fact equal to, then using the same power law in the denominator, n upon m times 1 upon log to the base b of a, but I do not like log in the denominator. So what I can do is I can do this as n by m log to the base a of b, again switching the sides, argument to base and base to argument. If I can do this, then I have established a new rule, which is log to the base a raised to m of b raised to n is equal to n upon m log to the base a of b, and hence the target we have achieved. Now how will I use this in our existing problems? Right. So let me write the existing problem here. So log to the base a of x is not a problem. This is good enough. Can I use this rule to convert this log to the base a square of x square? So in this problem I am asking a question: log to the base a raised to m of x raised to m is equal to what? So if you look at this carefully and if you look at this formula carefully, I am just replacing my n by m and b by x, and if I apply this formula, then this should be equal to m upon m log to the base a of x, which is equal to log to the base a of x, and this is true for all m. Therefore, if I look at my problem, log to the base a of x, a square of x square, then what I am actually saying is, I am slightly shrinking it, I am actually telling you that log to the base a of x plus 2 upon 2 log to the base a of x, this is my LHS, plus 3 upon 3 log to the base a of x, and so on up to p upon p log to the base a of x. What should this be equal to? This is equal to, if I use my power law, it is 1 plus 1 plus plus 1 into log to the base a of x, right. So, this sum, this 1 is appearing p times, right? It is appearing p times. Therefore, my answer to this question will be equal to p times log to the base a of x, which is nothing but RHS. So, I started with LHS, which is this, okay, and then I reduced it using this formula. I have used this formula, which is derived from this formula, and I got log to the this complicated expression to be equal to some simple term which is equal to this. That is the power of logarithm. So, let us summarize today's class. What we did, we started with problem number 6, in which we have actually demonstrated how change of base property can help you in solving the problems. After solving these problems, we went to the 7th problem. In that, what we did is we assumed this to be equal to some constant number and used the property, which is a special case of change of base property. We derived that property in fact, and we have solved the problem. 8th problem, which was a very tricky one, where only change of base was used and it actually reduced to a number 0. In the 9th problem, if you remember, we have shown some absurd logarithmic expression, multiplied logarithmic expressions equal to 3, that too using change of base property. So, any time the guess can be any time whenever there is a log of some expression into log of some other expression with different bases, the change of base can help. That was the conclusion of 9th problem, or in fact 6th to 9th problems we have been doing that. 10th problem was very easy problem. It was just an algebraic manipulation which we can do very easily. It just gives an idea how to do algebraic manipulations. In 11th problem, we have shown some relation to be satisfied. Again, we used rigorously change of base theorem for solving that particular problem. In the 12th problem, we have used another change of base property, and we derived the expression in a very simple manner, and we were able to show the relation. If you remember, that was log to the base AB of ABC and log to the base BC of ABC and log to the base AC of ABC. So, that also we have done. Third problem, again change of base, but the expressions were given in a complicated form. So, we first simplified the expressions of x, y and z and then showed that the relation is satisfied easily. This was a very interesting demonstration of the power of change of base. In the last problem, that is 14th problem, we have actually derived one power where the base has a power and the number has a power. Okay. So, the logarithm was of the form logarithm to the base a raised to m of b raised to n, and we showed that this can be equal to n upon m log to the base a of b. This was an interesting deduction of the change of interesting deduction from the change of base property, and showed that we can actually derive we can actually simplify many calculations if such a form exists, and the answer can be very simple. So, in particular we proved some relation based on this. Okay. So, today's class we have solved several problems based on change of base property. In fact, this lecture was dedicated to change of base theorem from logarithms. So, once again thank you for watching. See you in the next class.